seats, almost all the seats are taken, then maybe we can start. And I'm very pleased to welcome
Do you prefer if I were over there?
To give the brain seminar today. And we've also combined it with the Concordia Convergence initiative, because Patrick's talking about science of art and illusion. So we'd also like to welcome the people from Concordia. And I was just talking and remembering that I first met Patrick at a satellite meeting of a vision conference, which was also a workshop, and it was the same meeting in which I also met Fred Kingdom. So it was a very productive meeting, and I have to say, with some reservation, that was in 1988, when I was really young. Still very, very young. We were all very, very young, 1988. And so that's like 31 years ago, which seems, I don't know, not that long ago, really.
Like yesterday.
Like yesterday, yeah. And I still can remember the meeting because it was really interesting meeting. It was a workshop, and we also had a theatre, and we were doing. Patrick was doing lots of demonstrations. So Patrick has had a very interesting academic journey, and I think somewhere in your bio you called yourself an academic transient, but really you're an academic explorer, not a transient. And Patrick actually originates from Montreal. You did your undergraduate at Montreal in engineering at McGill. And I think even before that, if I can go before that, you were at high school in Montreal for a short time, or maybe for a long time, I don't know.
Grade 7 to grade 11.
Wow, okay, very good. At Westmount High, right?
TMR and then Westmount.
TMR and Westmount High. So he's a true Montrealer. After graduating in engineering, I think he became interested in AI, artificial intelligence, and went to do a Ph.D. in cognitive psychology in Carnegie-Mellon University. Then came back to Montreal, but to Université de Montréal, where he had a faculty position in psychology and was required to teach in French, which I imagine was a challenge, depending how well they taught you in Westmount High. I don't know.
Not at all.
Not at all. So it was a challenge. And I think I read you said that you were teaching in French in University of Montreal, and people shouted from the back, just speak in English. Which wasn't the common sentiment in those times, I think. Anyway, after that, then Patrick was recruited from University of Montreal to go to a position in Harvard as a professor at Harvard, and set up new vision laboratories in collaboration with Ken Nakayama. And that was very exciting times, doing lots of new, interesting research in vision. And he was there for quite some time, almost 20 years, before making a new and interesting move to Paris. In the Descartes University in Paris, he had a chaire d'excellence there. And after 10 years in Paris, returned to Toronto, and is now has a research position at Dartmouth College in New England, but is also at Glendon College in Toronto. Correct me if I've left anything out. And Patrick works in visual neuroscience in all sorts of different aspects, in motion, in particularly in attention, and is very interested in top-down influences, and in the representation of form. And he's been really a wellspring of creativity, and has never been afraid to take a different path. And in his journeys, he's been through all these aspects of vision, and now his journey is led into shadows. He's just published a book on the visual world of shadows. So as we all know in vision, we use our brains to create models of the world, and those models should be useful to us in getting us around the world, enabling us to survive and to live. And art creates models of our experience of the world. So there's a lot of overlap between vision science and between art and its representations of the visual world. And so I think that Patrick's going to try to blend together these two interests, and of all the people who should be able to do it, Patrick is certainly one of them. Thank you.
Thank you, Kathy. Can you hear me in the back? I think that's a yes, okay. How about, can you see the screen at all? Some? Okay. Yeah, so we'll take a tour a bit through some of the work touch very briefly on some of the work we do now, but mostly on the idea of using illusions, errors, perceptual errors, as a measuring method to understand how the brain works, or vision in particular, of course. So how does vision work? Well, this is the sort of immediately visual part of the brain, but there's about a third of the brain involved, at least a third of the brain involved in vision. And that's a lot of brains. We have a big brain. A third of the brain, our brain, is bigger than a chimpanzee's brain. So think of our visual brain as being really, really smart. I like to divide, as Mar and others did, vision into two parts. There's a first stage of measurement. We're familiar with lots of stages, lots of little bits of measurement. The retina does lots of measurement, and colors and motion. But the interesting part really after that, or the really important and much less studied part after that, is what you call inference. What do you do with those measurements? And what we're going to use, what we're going to talk about, is using errors of perception, illusions. Now, some of these errors are not, glitches or bad engineering. They're actually functionally purposeful, but they make what we see different from what's out there. So we use these perceptual errors to understand how vision works. So you probably know that kind of diagnostic anyways. You do that when you get a cell phone call. And you can tell whether someone's calling you on a cell phone because their sound breaks up every now and then. Or maybe they're on an internet line and there's a huge delay. So you use these errors to understand how that phone system works. Now we can do that with the brain. So let's get a general overview. Then is the brain. We have a scene in this measurement stage. You guys have some edges and colors, motion and depth. So little receptive fields are doing this all over the visual field. And then there's an inference stage, which does really clever deductions, predictions of what the surfaces are, what the objects are. That requires a lot of knowledge of what objects would be. Things like these edges from the shadows are not real object edges. You finally figure that out very quickly. And then you have this reconstruction of some scene that you see. But of course, our visual part of the brain is not the only brain we have, and there's a whole other part of cognition that can be the kind of witness. Oh, okay, so that's what I'm seeing. Is that really true or not? So unlike a stereo system or a cell phone, we can actually appreciate our errors and catch them in the act. So here's, of course, a classic example, the Mueller-Lyer. Those two lines might look, is that too low for you? I could lift, can't lift it up. The two lines might look different. The left one looks longer than the right-hand one. But in fact, of course, we got a ruler out and measured them, sort of like that. We find out, of course, they're physically the same. So that's an error that we can find out by using our cognition and tracking it down. Okay, so the measurement part, a lot of you know about and do these sort of things, like Curtis in the back, doing physiology of different parts of the visual system back here. So the information comes from the eye through the lateral geniculate to the first visual areas, where there's billions of individual cells, and each of those cells are kind of monitoring different parts of the visual world, a mosaic, each one saying, I have some red here, I got some color over here. So they make the measurements and tell us what's out in the world, kind of like a camera would, a very fancy camera, unlike any cameras we have, even better. Okay, so making all these measurements, some even to this stage of faces. This is not registered it's registered elsewhere in epilepsy patient, had a cell that like Jennifer Aniston. So these cells that kind of respond passively to properties or measure passively properties in the image can go as high in terms of complexity as a face. It liked Jennifer Aniston, didn't like it when she was with Brad Pitt, it was with Pamela Lee, didn't like Pamela Lee, so a very high order of specificity. Okay, well, we can learn about these measurement stages with just simple perceptual tests, looking for errors. So if you stare at that little dot for a moment, we'll get the classic example. When I get rid of the colors and leave them colorless, keep staring at that dot, you probably see some nice sharp colors there. Now that's kind of interesting, It's sort of the idea of the color after image where there's a component pair. And what that simple illusion, error, effect of how the color system works tells us which colors are paired together. Not just that the visual system likes to take differences between red and green or others, but it tells us between what and what. And in this case, you can use these to actually understand how the color system is wired. Or, of course, the idea is if they are paired together in opponency, if one is fatigued by looking at what we saw a moment ago, then the other dominates. And the same thing for emotion, a classic example here, Buddha, who is not moving, nice and calm Buddha. But if we alternate Buddha with this motion stimulus, looking at the center all the time, of course, then the adaptation of the cells of each location going inward, eventually, while you're looking at the center, makes Buddha expand as of course a Buddha should. So it's the same point that here, it's the motions that are opposed, left versus right, or here upwards to the right versus downwards to the left. And normally they are opposed, and normally in a static signal like this, static image like this, they are equal, so they cancel. But you just tired out one set of them, all the ones that were going inward, and so outward dominant. So we can understand a lot about the measurement stage from these simple observations of errors. But of course, measurement's not everything. So you have to have something else going on. And we know that from lots of classic versions of bistable stimuli, Necker cube, which you can sort of organize one way or the other. The recently famous dress, which to me is white and gold. Maybe there are others, we see it otherwise. Or depth from shadows. So here's a nice set of, looks like little chips of wood. But if we rotate it, you might have a different organization. As now, it appears that our visual systems assume light comes from above, and when you do that, you see this perhaps as some deer or stag sticking outwards in the background, whereas of course it was not that at all. So there's some assumptions about light helping us to disambiguate stimuli which are not really fully described in the image. So we get these image measurements, but that's not enough. You need inference, you need something really clever to make plausible guesses based on knowledge and rules, so some rules like where lighting is and so on. So we really want to know what these inferences are. So here's some of the work we do with perceptual errors in position, telling us about how the motion system builds up inferences. So this was Stuart Anstis, and you'll see a red and a blue flash. Now the red and the blue flash are actually physically identical. They are the same size and in the same location, and it's not easy to appreciate that until maybe I try and put my finger on the blue square. Stuart ran an experiment where he showed that the time it takes you to put the finger on the blue square gets really long. If you are, okay, that happens there. There, okay? Okay, so my finger's at the same location in both blue and red square. See, the time it takes you to put your finger on the blue square varies with age. A little bit longer. So the idea here is that this is in motion, and when it's in motion outward, the blue is flashed, and the blue, even though it doesn't actually move, is taken to be part of the moving structure. So it's in motion, and its perceived location is carried out with the motion, whereas the red one is flashed just before it shrinks. So its location is carried inward. Now what is that? Is that kind of an error? Well, this is a position shift, but it's actually has a functional purpose. It accounts for motion during the delay of perception. So our perception isn't instantaneous. We don't instantly become aware of what lands on the retina. There's about a 1/10 of a second delay. Well, a 1/10 of a second, not much, but in fact, for things that are moving, it's quite a bit. And what our brain does is attempts to predict where things will be given that 1/10 of a second delay. So we see things, if they are changing in a predictable way, getting brighter, moving in position, whatever, changing size, we see them as they will be after a tenth of a second. So that doesn't seem to be all that important for just ordinary perception, but I'll show you an example where it is in a moment. I'll give you the idea of why it's important for when you make eye movement. So saccade is an eye movement to a moving target. So here, let me give you a moving target. Hang on. There. Okay, so just move your eyes to it. Okay? Now you were looking somewhere, and you made an eye movement to the moving green target, and you probably were pretty good. So lots of experiments that show that, like you were, people are pretty good at landing their eyes on this moving target. But again, there's this at least tenth of a second delay between what gets to your retina and what you perceive. And not only that, there's another delay of moving your eyes physically to where the dot is. So if you actually programmed your eye movement to the location of the dot where you were seeing it at the time you're making the program, you'd land, it won't be there. It's moved on. So as Dan Guiton and others who do this work know, the visual system, the oculomotor system, makes that prediction of where it's going to be. Well, how could it do that prediction? I think you can see that it's an important logical prediction. Let's predict where things will be so my eyes go to where it is. But you could make the prediction by aiming ahead of a target, as in skeet shooting. Let me see if I have a bit of a noise here. And in empty space. Boom, okay. Those of you who don't, that's a clay pigeon, that's not a real bird, okay? You notice how he's aiming ahead. So if you've ever done that sport, you know that you have to aim ahead. So you're aiming in empty space. You know, you can do it with cars. So he was also aiming ahead. So that aiming in empty space, but that doesn't seem to be what happens. When you make your saccade, you feel you're aiming right at where it is and you land on it. How does that happen? It's like somehow there's some virtual target that's been extrapolated forward, and that's that effect of motion on perceived position. So there's this made-up target. You're not seeing it here, you're seeing it there. And of course, this is moving so slow that you're not actually seeing that tenth of a second shift. The gun has a much longer shift it requires. Anyways, you make up a target, and that illusory position shift I showed you is functional in service of action. I really like this example. So here's, yeah?
I was curious, does that mean that, let's say you never go onto this right wall, but you just stop before coming back, will we see it actually on the right wall even if it was never there?
Oh, will you extrapolate over the end?
Yes.
If you make an eye movement to it, you'll probably extrapolate beyond it. Perception seems to be smarter. It has some extra time and erases the overshoot. So yeah.
It will erase it?
Yeah.
Okay.
Yeah, it's kind of get edited away.
Cool.
If
So
you
my
catch it,
perception, I will never see.
we'll never consciously be aware of it, but if we do an eye movement just near the end, you will overshoot. Yeah.
Okay.
Okay, so this is Rafa Nadal, #1 in tennis. Many of you are great fans of his, I'm sure. He's going to hit this ball, traveling about 30 meters a second. Watch his eyes. Okay, so what's really interesting there is, when you get there, not there. Look at that, okay. So his eyes are pointing right at the ball. But remember, your conscious awareness is delayed by a tenth of a second. This ball was a tenth of a second away, which is 3 meters, 9 feet away, way over here somewhere. That's the information his brain had to get his eyes to look right at the ball. So his eyes have predicted where the ball is. He's looking right at it. But he's probably not seeing that ball at that moment because that's a tenth of a second away. But he's not seeing nothing. He's not like a zombie. He's probably seeing that prediction, the perceptual prediction of that ball from back here. So maybe it's a bit fuzzy. Not that we can care too much. Okay, so there's all this incredible prediction and changes in our experience of the world that are errors from the physical world, but they're not really all errors. They're in service of some function. How do you measure these errors and these illusions? Well, you can do all sorts of things like fMRI, get some nice images, you can do EEG, you can do all that, and that's going to cost you a lot of money. But there's another way. Okay, so that's what I'm here to tell you about, is how to do science for free. How to do it by looking at what artists have done. So artists exploit the processes of inference. They have to in order to make these flat images. Think of it, they're flat, of course. I mean, we take these things for granted, but take a moment. Paintings are flat and yet appear three-dimensional. Artists have had to figure out what our brains are doing, processes of inference, in order to make these illusions of 3D work on flat paintings. Okay, give this a sense of depth and light and that, of transparency, and she's wearing undergarments under her robe here. This is quite beautifully done. Okay, so this is what we're after. So I want to help you through this idea so that you can go out into museums or look at your favorite paintings or photoshopped works, whatever you like, and get science for free. So we're going to use the technique not just of looking for errors, which is what I was talking about in our scientific approaches with research methodologies, find errors, see what they tell us. Here we're going to look for errors that you don't see. Errors in art, where you're not going to say, oh, that's wrong, or you're not going to say anything at all. Maybe you just say, that's a beautiful painting, but they may be full of errors, and those errors are going to tell us about the brain. Okay, and the interesting thing about art, compared to a regular, picking up Google search or whatever, is that there's 40,000 years of documented experiments in vision by artists. And this is a real source of data for us, for how the brain works, that we can't ignore. And what we're going to do in that 40,000 years, we're going to look for errors that we don't notice. Okay, so that's why it's kind of fun. Because first of all, you don't notice them. And then you think, or you look again and think, oh, but that's not right. That's not physically correct. Why should that work? And then you get a clue about how the brain works. So that's the idea. You're looking for what looks okay but shouldn't. And these are shortcuts that work even though they break the rules of physics. And these shortcuts that break the rules tell us what rules the brain doesn't use. So we can kind of figure out what rules the brain uses and doesn't use by looking at what mistakes artists have that we don't notice. They go, oh, I don't have to care, say, about light. I don't have to make the lighting correct because nobody really knows this. I'll arrange the lighting so that it works best for the painting I want. So this is science by looking. It's free, which in these troubled times of low grants is good. Okay. Now, a lot of people, some people say, well, you can't really learn much about the brain from art. You can use science to understand how art is made, maybe, or why artists did it some way or another. But how can you use art to tell us about the brain? Because someone like Gibson would tell you, well, paintings just copy, realistic paintings, just copy what would have landed in the eye anyways. So what's the big deal? They tell us nothing more than a real scene or a photograph would. So let's just go out and study photographs and make our real scenes and computer images, but not worried about art. There's nothing extra in art. Well, that's totally wrong. I mean, it's true in some cases. For example, perspective. Okay, now in the real world, the parallel lines converge. Okay, they're converging that way for me, but for you out there, they're converging the other way. That's how it works. So that's perspective, and it's in the real world. And then, lo and behold, the Renaissance painters discovered how to put perspective into art. And that's useless for us. It's beautiful for the art, of course, because it's more depth. But there's no error there. It's just copying. So that's the idea that things in art that just copy the structure of the real world aren't telling us about the brain. And we might as well study those things in photographs or out in the real scene. But there are lots of other things that are errors. Now take line drawings. So line drawings are part of our culture forever. And just don't think about them much. But in fact, it's a good question. Why should line drawings work? Now, there are no lines around objects. No lines around this here. There's no line here. What's the here? It differs it from the background is a change in luminance. There's no line. But I could make a sketch of this with a line around it, and it'd be perfectly fine for me. How could that work? So that's it. Take things that you take for granted and ask, but maybe that's wrong. Why should that work? And then see where it takes you. So I'll take you through, oops, sorry. Okay, so the line drawings are not realistic, they work, okay. I'll take you through 4 kinds of tests like this, but I think you get maybe even after 1 or 2 the whole idea, and have examples of your own. You can maybe add to the mix. Okay, so we'll look, first of all, the biggest illusion of art, of course, is flat things look 3D. It's clear we didn't evolve with paintings around us, and that our brains are organized so that they're just hungry for 3 dimensions, because that's the world they have to live in, and they look for all the cues possible to build a 3-dimensional structure. And if it happens to be on a flat painting, now that we have paintings, well, fine. We take those, even though we can see that it's flat, that doesn't veto it, we get the depth. You can look 3D. But there are some interesting constraints to that, and I'll show you. Also lines, I mentioned line drawing, so lines work. Here's a really old line drawing. We'll look at how paintings can just be sparse, as you know. You don't really have to fill in everything, and that tells us something. And then the part that's interesting really for me most recently with shadows, that's one of my favorite interests, is how light, shadows, and reflections are captured by painters in ways that break so many rules of physics without us noticing. And that really gives us a hint about what the rules our visual system uses for those light, shadows, and reflections, what those rules are. Okay, well here's like a little brief glimpse of how this process works. But this is for birds. This is a really cute bug from Central South America called the peanut bug, because his head's kind of peanut shaped. He has this marvelous mimicry on its wings. They look like eyes of some scary monster, scary weird bird, and it has this reflection on it. So that reflection, so it's all fake, of course, right? And also the most fake part about it is if I move past this bug, the reflection doesn't move. As you know, any reflection on a curved surface has to move with you, otherwise it's painted on the surface. Okay, so clearly birds' brains don't have that part of physics built in. They are fooled by this, as are we, and that gives us like a hint. So you have an idea of how this works here, and this is on evolutionary time. Painters haven't been working quite this long, but found many of the same points. Okay, 2D looks like 3D. Obvious, lots of books on this. Cool part here is if you notice, Salvador Dali is looking at each and every one of you. Now, if he were a statue, that wouldn't be true. So 2D, paintings are flat, can be viewed from all angles. That's the amazing part. So this isn't just capturing physical reality. This is going beyond physical reality. It has a property that you may not have thought about, but is discussed in lots of textbooks incorrectly. But this point is, they look pretty much okay from lots of angles. And proof that it is, of course, that Salvador Dali is looking at each of us. No matter where I stand, I can't get away from it. He's still looking at me. I'm over here, still looking at me. Now what is that? And that's in a sense 2D being better than 3D. These pictures give us a shared experience, independent of the angle. It wouldn't be true in a play or a sculpture, 3-dimensional sculpture. So what's the problem? Well, we know that all these cues in an image, like occlusion, perspective, and so on, support a 3D interpretation. But why aren't we disturbed by how these paintings viewed from different angles look? If I move around, the whole thing should compress, and the 3-dimensional structure I recover should start grotesquely changing shape. But it doesn't. What's going on? Well, some people say, this you will find in a textbook, that you correct for the angle of viewing of a painting by seeing the frame and computing what it would look like if you were standing in front of it. Because that is so much nonsense. The mathematics involved, and the idea that you would have evolved this response to paintings in the last couple hundred years, 1,000 years, for something that never existed before, it doesn't make any sense at all. So it's probably not right, but we can test this. Let's give it a shot. We're going to take pictures with more than one angle. This is a favorite illusion in Canada, around and elsewhere. So I'm not even going to show the real version of it because I know you've already tried it on your own $20 bills. Now I'll show you one. We did this a while ago, as you can tell, on a well-known ex, as we hope others are soon, Prime Minister of Italy. Now we took his face and printed it on a surface and made it kind of a W shape, so it bent out and bends back, as I see when I tilt it. Now you're going to tilt it. Okay, so there's some surfaces on here, and now when you tilt them, if you were able to judge what the frame angle is and see it from the front, then there should be no change here, because of course the picture didn't change. Now, let me emphasize that if I had the real picture and did that, you get the same effect. There he's back again, and there he's tilted the other way. Okay, so it's clear that we're not correcting for the surface angle. We just take a look at our retina and we interpret the pictorial cues in that. Very straightforward, very simple. So bent pictures don't work. No correction for picture slant. That tells us something really deep about why flat pictures are so interesting. They work because our internal three-dimensional representation isn't really Euclidean. It's not really 3D. It's some kind of cheaper version, quicker to compute, good enough for reaching and doing things and interacting with the world. Some of you might like affine transformations or other, kind of 2.5D. Something's going on that makes those pictures, flat pictures, look pretty much the same from different angles. And it has something to do with the math in our head. And its advantage is it gives us this indifference to viewing angle. So that wasn't of any value until along came paintings. And all of a sudden, not only can we make paintings, but look, we can all share them. We don't have to have one special seat in a movie theater. Most all the seats work pretty well. So a lot of our visual culture depends on this tolerance to different viewing angles. That reveals a bit about our internal representation of 3D. Okay, line drawings. You know this is an old painting, right? Cave drawing, because there aren't any mastodons around anymore. But there were then. And what's striking, what's stunning about this, think about it, is this is just a line. If I just showed you this line in isolation, it's just a line. But when you see the whole object, you get the impression this is an object in front and that's a background. This line now stands for an object edge. So that's not something, that's something really important. That made line drawings work. That the line can stand for a change of object from front to back. Now this kind of lines around objects are super rare in the world. You hardly ever see them. You have to backlight someone. I think you know who that is. I think you know who that is. There's the thing about these silhouettes, though, is there's no internal. She has some kind of glow on her earring. There's no internal lines, so we're not unfamiliar with silhouettes. They're pretty rare, but we are completely unexposed to things with lines in the internal structure as line drawings work. Why do lines work? Well, we know from physiology that there are oriented detectors in the visual areas. They like, let's say, light here and dark on both sides, and they might line up. Their job is to find where things are light or dark in the world. So they might line up and say there's an edge there, some edges there, another one there, another one there, another one there. So trace out all the edges, but when you put them on the middle areas, where do you go? Come back there. There are no edges here, so there'll be no response here, but there'll be responses at the edges. So this was Hugo Weasel's original work, of course. But that means in the visual system somewhere there's some kind of sketch of the edges of that cube. Now, of course, it's all distorted by the way the visual system represents space, but it's like that. Now, if you replace the this, which is the line drawing, well, the same thing is going to happen, of course. This, even though it evolved to get edges of light to dark, works fine on lines, just by chance. It wasn't designed to do that. There weren't any evolutionary pressures to do that, but it just does that. So it gives you the same, and so there you go. Design evolved to detect edges, it responds to lines as well. But that's not it, okay? That's not really the whole story. That's certainly the start. What's really interesting is the point that not all edges and lines are useful, and anyone who started or did computer vision and analyzes an image knows that 50% at least of the lines in the image are just shadows. They are illumination errors or artifacts that are not object edges. So that's the image. Here are all the contours. What are these things? Well, you can't know unless you understand what shadows are. So lines alone doesn't explain why line drawings work. The fact that neurons respond to lines like they were edges doesn't explain why line drawings work. There's something else that gets us to the real meaning of this image, and that's that the brain knows which lines are object lines and which lines are not. And we don't actually know how the brain knows that, but we also know that artists know, because artists, if they give that, say go to a sketch, they draw that. So artists and brains know something, and when we do study artists, we try to figure out what it is they know and how that can help us understand the brain. But that's why this is interesting that line drawings work. And it's not just solved by a simple similarity of response to edges and lines. But you could say that's all irrelevant. That in fact, we only understand line drawings because it's a cultural thing. This is what our culture does. This is how we communicate. It's like alphabets. Alphabets have arbitrary shapes. How do you know that an A means that? Well, because you learned it. If you were a newborn infant, the A shape, be careful when I say that, the A shape, or the B shape, the B-ness would be evident after you learn to read, but not before. So there's a cultural convention. Now maybe some lines are. So odors here, sound lines, Keith Haring's animated Space Alien. All these lines are perhaps something we learn and wouldn't be innate. But other lines are. These things like occlusions, T-junctions, these seem to be known because all cultures respond to line drawings. In a nice study done by John Kennedy and others, when you ask the right question, you get that all cultures give you a common response to line drawings. Babies respond to line drawings of faces. Monkeys do. Single cells do. And bugs do. Well, actually, this tells more about a bird, right? So here's that same bug, but look at its head. Look how it uses a line here to differentiate the lip from the mouth. Okay, so somehow it's pretending to be some scary caiman or South American alligator, a small size, and clearly this has worked because it's still around with us and it has used lines to represent different surfaces, and that worked for the birds who decided not to eat it. Okay, so for lines, they work because edge detectors happen to respond also to lines by chance. So artists discovered that this is good. It lets you make shapes with minimum effort. And now we can use some of this and some of the artist's understanding to understand which scene contours are critical for visions. That's as far as I'll go there, but you can see line drawings are really open area, of real interest both for art and science. Sparse, I said images can be sparse. Well, some of the sparses, of course, are impressionist drawings, paintings, which look full of space and light and human beings. So there's not a lot of detail here, and yet it's enough to give us the impression of seeing lots of details. We fill in the gaps of what we know about what human bodies would look like and what wind might do to a veil. So this is really access to memory. So some of the paintings can tell us a lot about how memory is involved in our immediate perception. Like this poor little boy really has no nose, but we didn't really notice because it got filled in. How does that work? Well, here's two circles. It could be anything, right? If I asked you which was in front of the other, that doesn't really make sense here. You don't know. It's ambiguous. But if I put some very schematic clues on it, it seems to be a face. And so now we do know about faces. That the mouth would be, of course, out in front of the bounding contour of the face. So that this must be behind that. We have some depth here. So the idea is some of these clues are characteristics, some kind of eye shapes or characteristics that sort of light up this idea, okay, this must be a face, let's check. Is it a face? Well, kind of a sketchy face, but yeah. So our first guess of face looks okay, but perhaps it didn't look okay. Then we reject that and find something else. So that's kind of how we're doing object recognition. And I'll give you some examples of the most minimalistic images. These are two-tone images, and these were really only discovered by Giorgio Kinyork in 1899, some earlier ones. And he just used two levels. Of course, these are now everywhere in our culture for all sorts of graphic design and art. But the point is, there's no difference between the dark shadow and the dark pigment, the dark hair. And it kind of breaks everything up into different zones that aren't really that related to the object. So these are really good tests of how we recognize things. And the standard model recognition is we have an image, we look for some contours, we find the parts, arms, head, legs, and so on, and put them all together, and we check, okay, we have this thing, what could that be? What's a teddy bear? We get the object. But this says that's not what's happening. And we have some real understanding of little two-dimensional images that land on our retina, just the contours themselves that are characteristic enough of a face in this case, so let's go, oh, must be a face. Okay. That's the only possibility. It must be a face. But then we have to check. Is it really a face? Perhaps it's not. In this case, it is. We get the face, it looks okay, and we're done. That happens in about 1/10 of a second. So you're not even aware of this 1/10 of a second in which you're checking, computing, possibly a face, okay? I'll give you some examples where we can see that you're looking for features. Okay, I think it's a face, check it, accept or start over. So I'll give you some that are where you're going to have to start over, so maybe experience this step of confusion that we normally avoid and we see everything pretty much directly. Okay, so here's one. So the idea is something's going to happen, we get an initial interpretation, and then a split second later, you hear, oh, no, that was wrong. You'll probably never be able to get back to that first interpretation you had because you just replaced it, it's edited it away. So it did take, maybe it took me longer than any of you here, but it took me a while to figure out that was a dog wearing a man's clothing. I thought there was a man and a dog. Or here, where the distinctive feature here is the shoes. The shoes, okay, it must be feet. Those feet, well, they have to be legs. Oh, that doesn't work out. So eventually you just you recompute and start over. So the idea is that's going on all the time as you recognize objects. And usually you get the right answer first and off you go. Or this one, I like this one. So we have a model, we have an internal model. Object knowledge for bodies includes, bodies, heads, and so on. This looks like, the head part doesn't connect to the body. And especially because you got red hair, you should have been wearing green swimming trunks, so that makes sense. But then, of course, it can't work. So, but that's like a grammar error in vision. Just, and then, oh no, okay. So you've got the idea that this is a rapid use of memory to recover stuff, body shapes, clothes, and so on, and build an image in which you then either accept or reject. So get best guess from memory, check for match, accept or start over. Okay, now we look at, as I said, my favorite area. And the reason I really did start to get interested in art was because we were working on shadows. And just, how do you know the dark area is a shadow or a hole? Or how does that work? And who was the first artist who used that? And okay, so we spent a lot of time and tracked a lot of this down. And I'll share some of that with you on what artists understood about what they can get away with shadows and light, and they can get away with a lot. And that's telling us a lot, again, about the brain. So here's a really old painting. This is painted by a Greek painter of a dead Roman in Egypt. These are the Fayem portraits. And why I love it is just these, it's very modern to me. I mean, be surprised to see it in someone's house. He has all the techniques, the highlight along the nose and the eyes, highlights on the hair, shadows under the chin and the nose, very three-dimensional. And this is already 300 years, 400 years after the very first shadows were starting to be used in Greek paintings. Or this one from Pompeii. This is stunning feeling of depth with the robe is just a bit above her leg, and you see the shadow cast by the robe on the leg. So they had it all. There's some things they didn't quite get, but they started it and understood a lot about it. Over time, under Roman hands, the shadows kind of deteriorated. So you have to have shadows to show that the feet were on the ground, but they kind of lost their way, right? And made these funny, strange shapes that were meant to be shadows, and people at the time would say, oh yeah, that's a shadow, but don't look that at all to us. And pretty much after that, shadows disappeared from art. Cast shadows disappeared from art for 1,000 years. Paintings were like this. This is also perhaps the first athlete in a bikini. This one here with no shadows by the feet. And it's not clear why there were no shadows. Some say it was kind of a religious choice by the Byzantine church. Others have other theories. It's cloudy. We don't know. After 1,000 years, boom, in 1 year, 1425, 3 or 4 different painters, some in Flemish, Netherlands now, and some in Italy, just became all of a sudden photorealistic. There are some ideas about it, but the point is they brought back shadows in a stunning way. I mean, look at these little shadows here. Well, let's look close up. He's using double shadows because there's 2 windows, so everything has a double shadow. And there are also some nice highlights. You see the 2 windows and the highlights and the shadows. These are stunningly realistic. All of a sudden, nobody knows why. So you can come up with your own theories about what happened in 1425. Something was going on. Okay, so cast shadows return, and this is a super famous painting from the Renaissance. A little bit later, because of its mastery of perspective. It's got all the perspectives going to a vanishing point, which is kind of over here. And this is in all the art history books. This is an amazingly famous painting, which is, I hope you'll see, full of egregious shadow and lighting errors. But you don't, because it's a beautiful painting. Nobody says, oh, he really messed up. Let's look. So lovely shadows lit from the left here. Look at these cast shadows here on the ground here. But there are no shadows up here. There are very few, if any. Okay, and in fact, if you go to the Metropolitan Museum, I think that's where I saw it, you see this is a grid of pillars that should be casting a zebra-like set of shadows in here, which the artist just didn't bother to do, and we don't notice. But the real crimes are here, in this beautifully lit room, but lit by what? So where's this light coming from? There's only one door that would let light in, and it's not doing that. Not only that, but what are these? Look at these shadows going upwards here. Okay, so the point is not, oh wow, those are really wrong. The point is, this looks pretty good. This looks beautiful. And the point is, of course, that the artist had his own intentions about how to lay out the scene, how to make, now this is the baby Virgin Mary getting her first bath, how to make her visible. She'd be invisible if he'd done accurate lighting. So he got away with a lot here, and that tells us about what rules vision uses to know what's a shadow and what isn't. So, first of all, shadows. Why do they bother putting them in paintings? What are they good for? Well, they add all sorts of depth and structure to an image. And so you have to, first of all, know that it's a shadow, and then you can use it to recover space and depth and so on. Here's an example. Here are these 4 balls, but they're all identically sized and positioned, but because of their different shadows, so this ball owns that shadow, that ball owns that shadow, they may appear to be slightly different in size to you. They're physically the identical size, of course. So there's some kind of organization of depth. This one seems to be further along. This one seems to be the closest one here. Here you can recover shape. This is the door to a tennis court, but you don't see it from this angle, but that's there. Now you could do that sort of cognitively. I don't know, perceptually you see that right away. But you do see that this is a set of steps, and that's the surface where the revealed by the shadows falling on the steps. You also see that this is a darker area. This is a shadow, so the light here, you have to compensate for less light. And this is still the same white surface as that, or light gray tile as that, even though the amount of light is completely different. So once it's a shadow, all of these things magically get used. It's very important for vision. And then unfortunately for the poor shadows, we now kind of throw them away, right? So if you were in this room and then you walked out of the room and I said, oh, where were the shadows in that room? You say, what? Not only had you not noticed them, you hadn't remembered them, but they're everywhere, right? There's shadows under the shadows all over the place. But you wouldn't remember them because not only do you not remember them, you don't really see them that much. You play the role and then they get tossed out. It's a bit sad. Okay, so shadow has to be darker, flat, and make X junctions. I'll tell you what that is in a second. Okay, so look at look at that shadow. So it makes this blue square seem to be up in front. I think you agree that that's what we see. And that's because this darker area is taken to be a shadow because it has all three properties. It's darker, it seems flat, it doesn't have any volume of its own, and it has X junction. So here's an X junction. Close up, see how this is a shadow border and this is a background pigment border, and they make an X. Well, that's a plus. Okay, call it X just for fun. Okay, so that's an X junction. There's lots of X junctions around here. This is darker, flat, has X junctions, good shadow, and it gives us depth. Visual system uses it for depth. Over on the right, it's also flat. This whiter area, it's also flat, makes X junctions, but it's not darker. So it has no shadow, and it doesn't have much depth. I think you agree, it looks like the blue square is kind of pasted on the background. Okay, so that's what's going on. The point is, if these three properties, darker, flat, and X junction, are true, most other physical properties of shadows can be ignored if you're trying to render, to depict, to paint the shadow. And so painters go to town, so it could be the wrong shape. That's a beautiful shadow, of course. It's nice and flat, darker, but there's no key there. And yet, you cannot unsee it as a shadow. It's a shadow. They could be the wrong color. So I don't know if you know those crazy painters that used odd colors, using wrong colors for the shadows. It's still a shadow because it's darker, it's flat, and well, I don't know if we have any X junction examples. It could be the wrong direction. This is Signorelli. He's the master of crazy shadow directions. Most of his paintings have shadows that don't make sense, but are fine because this tells us, this here tells us that his foot is touching the ground because his foot touches the shadow. It's a contact shadow. That locates his foot in the scene. And same with this man here. But he didn't pay attention that this shadow should have come this way. There's no reason for it to be there, but it still does its job. What a Taj Mahal. Okay, it looks good. I don't know if you've been to the Taj Mahal. I have not been to the Taj Mahal. But you will never see the Taj Mahal look like this. Because there's, whoops, I'm sorry. Back up. Oop. There we go. Because the shadows in the alcoves are the wrong way. So these ones are on the left side, this one's on the right side. So there's a complete violation of illumination direction, which is actually very hard to see. And we've done experiments on that. And by hard to see, I mean like 6 seconds for people to find in a variety of these odd illumination direction stimuli to find the one that's odd. Okay, so you can make lots of mistakes, get away with them. Here, this is a cast shadow. This is Betty Boop, of course. Now you can see that these work as shadows because they're flat, dark, and they're going to work even though there's incorrect lighting and shape information. So here, see how when she bumps over, when she goes over the trunk, there it is, yep, she separates from her shadow, and that tells us the depth. So that's why Disney animators use this. So this wasn't Disney, this is Betty Boop, can't remember. Okay, so look at these shadows down here. See how they don't touch the feet? That tells you they're in the air now. And as they start to move, well then every time the foot touches, now these shapes don't really match That's okay. I think you'll notice in both these cases, why are they shadows? This is snowing. This is in a cave. And yet these are shadows that work to us, to our visual system, despite having these illumination inconsistencies. This is my favorite one. See these little shadow spots? They tell us how far away the foot is from the snow surface, and they work. But there's no way that you would ever get this physical shadow to be an isolated spot. And it has to have a leg part, it has to have something else happening. So again, it's snowing. It doesn't seem to matter. Okay. Now, it's not true that you can get away with anything. There are things we notice. Here, these officials are checking out a roadside. Probably weren't there. And it's only because it's just missing slight smudges of shadows onto the road. It tells us even though it's an overcast, there's still slight smudges of light right near the object where it touches. That would have anchored them to the road. Or this one, which some of you may have seen, looks wrong, even though this is a real picture. This is in Hawaii at noon, at the moment, the day when the sun is directly overhead. So the cast shadows don't exist. They come straight down the pole, and there's no shadow. So it too looks weird. So we were even capable of detecting what seem to be inconsistencies when it's a natural scene. So we have these error detectors that kind of do some job sometimes. Here's one. Okay, so this is me, and I'm lit from the right. There's a shadow behind me. I just flipped my head around in the picture, and so I'm now lit from the left here, but my shoulder's lit from the right. That's kind of okay. How much can I get away with? Well, not that. Okay, so somehow all I did was flip the shadow on the nose. Somehow that just doesn't look right. So these inconsistencies of illumination, which seem to be acceptable in many, many cases, have some limits. Apparently, they can't be inconsistent maybe within one surface. Not quite sure about the limits to that. But there are limits. Okay. Now, a shadow needs an owner for you to get the depth. Each of those shadows told you about the depth. The distance from my hand to this. You have to say, well, that's the shadow belongs to this hand, not this hand. Tells you how far away this hand is from there. I mean, each shadow needs an owner to get some depth information. So the owner of that shadow is that square. And this is Rembrandt, and he knows that. So he's got this shadow here of the hand, and you can see the hand, and that kind of helps you place this man relative to that man. He must be a little bit in front for the shadow to be going down that way. So we see that as a shadow, not as a stain, right? Or here, unfortunately, it didn't work out so well. So again, there's a shadow. But because it's hard to detect the hammer, Thor's hammer here, casting the shadow, we can see the dark shadow it casts, but we can't link it to its owner. It has no owner. So, well, I guess it's not a shadow, so sorry, it must be a stain. So without clear ownership, the shadow loses its character. So you'll find in paintings, artists are always careful if there's a shadow to make an owner. There are only a few exceptions. So light and shadow has to be darker, flat, make X junctions. Now the reason for those, that small set of rules among all the possible physical properties that could have been chosen, is that it's local computations. They can be computed quickly. Don't need to have correct color, shape, constant directions. You don't have all these other features which could have been computed, are computed in computer vision, but they require much more computation. So artists discovered these rules. Well, okay, the visual system discovered a set of rules that was mostly good enough for almost all conditions, and artists discovered what those rules are and what they didn't have to follow. When should I stop?
How much more do you have?
Well, there's this one section I could just jump.
Okay, so 5 minutes.
5 minutes. Okay. Okay, so I'll squeeze a bit of it in. Okay, the same points I said about shadows hold for reflections and mirrors. They're very complex. There's only a few rules. This looks like a nice shiny toaster, even though the reflection doesn't match the object. Same here. This is a nice shiny beaker. Looks like silver. But the reflections that are painted on it to make it look like silver have nothing to do with what's in front of it. They are not what would be there. So the highlights off. Now, the interesting thing is there's kind of two kinds of reflections in the world. There's things that happen naturally, and there's things that happen recently since we've got mirrors, vertical mirrors. Now, only humans and a couple others recognize themselves as vertical mirrors. Other species attacking this. Monkey, as some of you know, was raised for 15 years with a mirror in his cage. Every morning he'd attack the mirror, never figured out that it was him. And there's a million, of course, little cat videos on the internet about how mirrors look like that, right? Right there he goes. Go on. or this baboon, someone tossed a little hand mirror into it. Okay, so there's something about these mirrors that only we get. It's part of our culture. In fact, painters use this a lot. You think this woman is looking at herself. Well, of course, the optics aren't right, or she's adjusting her earrings. That can't be true because we see her in the mirror. If we see her, she sees us. She cannot see herself. But the kind of convention is you put the person in the reflection to make the idea that it is a mirror. Okay. Now, it's different for flat things, flat mirrors. And what are flat mirrors? Well, water is a beautiful flat mirror. Of course, you recognize the Market. All the reflections are vertically aligned. There's this vertical symmetry in reflections on flat horizontal surfaces. So what about paintings? Can painters get away with something there? In fact, not. Every painting you'll find, the reflections on a flat surface follows the vertical symmetry rule. All objects are reflected as they should be. And you can look at any era. Matter of fact, if you violate that rule, it's not water. So that's something you can't violate. Only because, well, you know, lots of birds fly into horizontal buildings. They think the sky reflected in it is real sky. Lots of them, millions die every year. But you don't hear about millions of birds drowning by flying into flat water surfaces because they know about that. You can put a mirror in a parrot's cage like this, and they will attack it. You can put it on the floor, and they won't attack it. So there's a difference between vertical mirrors and horizontal mirrors. Okay, what did we discover? Artists really unlock a lot for us, and there's a lot more there. I hope you get out to the museums and you kind of try and use this idea, look for the mistakes you don't see. And we learned that internal representation of the world isn't really 3D. These folded images change in ways that couldn't be explained otherwise. Lines are a backdoor access to objects. Vision only needs hints. And only subsets of rules of light and shadow are needed. Artists can make the rest. So really, visual artists are our first vision scientists. 40,000 years of work, stunning work, and there's much more that they've discovered that we could probably unlock if we took the time to look at their work. So thank you. There's our book. Sorry, I went a bit over there. Yeah.
Thank you for an amazing talk. I was wondering actually, in that example you had of the shadow on the square basically being bright instead of dark.
Yes, the white shadow.
So you could basically conceive of something illuminating, right? Like basically a lamp or a light source or an LED panel.
Yeah.
It's just that we really don't have much experience with those. When you see it in some sci-fi
Or you think of low riders, you know, the cars with the lights underneath them.
Yeah.
There's a fringe of light around them. So I think there's something there, and it could have been. I would not have been upset to find that some people saw depth with the light fringe. I think that could make some sense, but I don't. So, and we did run out of subjects, and they didn't across in general. Just for that, I'm sure that there are probably other examples that look like light source underneath, giving a fringe around. Yeah.
But I'm wondering if it's as simple as basically using the size variation with the ground plane, so that any signal could potentially be that, so long as it.
Yes. So you have this square. Like you're saying, you have the square, and then you have something behind the square. And you could have put any number of things behind it that already gives you some occlusion cue that there's this and there's something behind it. So yes, I was surprised that the white one for me just seemed to make the blue thing seem flat. Could have offered a bit of depth, and I think if we put maybe some, instead of that white piece that looked transparent and flat, perhaps we put some like a dishware or washing machine, then clearly the blue square would have to be much higher above. So perhaps the fact that the blue square looked flat was because the white piece was a flat thing itself. And giving it some volume would necessarily bring the blue thing forward. Yes?
Thank you for a wonderful talk. I enjoyed it. It seems like your work, and I read one of your papers, and I'm sure it's in the book as well, looks at historical artworks and how they in their time discovered rules of visual perception, and then scientists looking at artists. But is there any examples of artists working with scientists to push those boundaries today, to maybe even discover more now that they've realized there's this joint
There's a couple.
collaboration?
There's Robert Pepperell in Cardiff, who does some lovely work on vision in the periphery. I mean, there are people like James Turrell who really are scientists of vision. They don't actually work with scientists of vision. They could, but they've already gone so much farther than the anyways. Other than Robert Pepperell, I'm not aware to many.
Do you think it's a nice future direction, I guess? Would you promote it to artists?
Well, it's such a different form of communication. Artists have this intuitive understanding of the world and how to represent it. It's not clear that they need or want some way to express it to others, other than through the paintings themselves. Some do have, visual scientist friends and buddies, and they talk about things. Some of the early artists did that. Certainly the Impressionists, and then after that, there were definitely influences from psychology and vision.
Other questions?
Perhaps. Since my excursion from eye movement studies to vision, I'm really struck by how little we know about vision. And what I find rather amazing is that you take chess grandmasters, for example. They don't necessarily scan a chessboard. You just flash it, and they seem to know. And the same for radiologists. Expert radiologists don't scan the image. So would it be correct to say that what we're doing, we're storing many, many models of different things that we're storing? It seems like millions of models. And so we're ready to accept a scene which fits approximately to a model we have, and we don't really care about the details. Would that be a reasonable one?
Well, the details create the basic information for that model to grasp the scene, but once it's done it's really directing what we see, and directs a lot of the errors we, of course, are led to. What's interesting is that artists, we did test some artists on a question like that. What is it that they do better than we do? So take an artist that has 10,000 hours of practice of sketching realistic scenes. What do they do better? Well, they don't. We test, so we find that they don't see differently. The world looks the same to them, but they remember and they grasp scenes much more efficiently. Like the chess expert that can look at something, that can walk around and can draw, and they have some kind of memory of visual structures that's highly developed and much more than ours. I guess like a musician would, to understand the chord structure, like all of a sudden, whereas for us it's just kind of a free tone.
It's learning a visual language, isn't it? Because it's a pictorial, it's also a representation that symbolises meaning.
And now that you're aware of that and you have looked at painting, do you still get fooled all the time by those illusions? And now that you're more aware, your brain is kind of looking at this right away? And is it different?
Thank goodness I'm always taken in, yes. Yeah, so painting, even if I now understand some of the things that they get away with, it's still beautiful painting. Okay, I still appreciate it. But it does give a chance to go look at a painting a second time. You go back and look at that, and I look at that, oh, you did that, she did that. But then I'm still in front of the painting and really appreciating what the artist did. So it's a pleasure. And so it's like that you and I are illusion, knowing that the two lines are different physically. I'm sorry, two lines are the same. Doesn't make you see them differently. So knowing what the illusions are that the artist has used doesn't change the power of the work. It won't make the magic go away.
You've given so many really beautiful examples, and I'm looking at your book cover here, and to me, the left to right gray seems to be a gradient. I was wondering if there's an example there. it looks to me darker on the left and lighter on the right, and I'm wondering whether
That's
it's the
illusion.
shadow
Yeah.
or the object or
You discovered an
illusion.
illusion.
It's illusion from this white part here is
From the
making this
white,
look
okay.
darker, yeah.
Thank you.
So, no, it is uniform.
But it's not the motion of the boat or the relationship of the shadow to the boat. It's the white on the left hand side.
I could have put more in.
Yes, Hamza?
Could attention also play a role in the fact that we can't catch errors? In
Sorry, say that again?
Could attention play a role in the fact that we can't pick on every single errors in shadows? For example, you showed a picture of yourself where you had changed the nose shadows. So it could maybe the fact that it's really local and really close together that we could pick up on the difference in shadows.
Yeah, so you're saying, is it perhaps the distance that
Yeah.
makes us notice the inconsistency? So we have not done that work. So if you're interested in that work, go for it. So we don't know whether it's because it's on a single surface, because it's a single object, or simply distance. All those are possibilities. But at some point, the inconsistency just jumps out at you, and we'd like to know why that is.
I also have another question. Is there computer science models of this non-Euclidean 3D representation?
Is there a computer science model of?
The non-Euclidean 3D.
Oh yes, there's lots of math on non-Euclidean 3D, yes. But if you're interested, the versions to track down that I think are interesting are affine, which means invariant to stretching. So a square and a rectangle are the same thing in affine transmission.
Yeah.
Affine transmission.
I would guess that faces have extra set of rules. I mean, I think you showed the
Sorry?
face. You showed the
Faces.
face example.
Yeah.
I think the face would have this extra set of rules just because there's so much visual processing
It might,
specific
yeah.
for faces, right?
Yeah. So if we did that shadow inconsistency with a non-face, with some like pegs out of a sphere, you might get a different answer than for a face. You're right.
Very quickly, just a little point. Mike Webster, in a piece of mine that he was reviewing, said that we shouldn't think of after images as errors, because rather we should think of them as real images under different states of adaptation. And of that, I guess you could argue that's true of all after effects. Do you think that's a valid point?
I think after images and after effects are kind of consequences of the engineering of the system. So, yeah, I wouldn't call them errors. They're just like, oops. They left over residue. Kind of like, when you eat a fine meal, sometimes things happen.
Any other questions? But just before we thank Patrick, I would say that we're going to move up to the seminar room on L11, where we'll have lunch. So if you have any further questions or you want to chat a bit more, and you can find someone to use the swipe, or you have the swipe, then you can come up to the L11 seminar room there. But now I'd like to thank Patrick very much for his really wonderful talk.